afternoon everyone. Today we are going to see about Lyapunov stability analysis of robotic systems. The outline of this lecture will be as follows. First, we will be seeing the Lyapunov stability theory. In that, we are going to see the concept of stability. Then we are going to see about the indirect method, which is also called the first approach of Lyapunov stability. And then we will be seeing the second approach of Lyapunov stability analysis, which is called direct approach. Then we will be seeing the examples associated with these two methods. Next, we will be moving on to Lyapunov function based control of robotic systems. In that, we will be seeing two examples. One is the single link manipulator, another one is general n degrees of freedom robotic systems. Now, coming to the concept of stability analysis, let us talk about that. Let us consider a non-linear system that is given by x dot equal to f of x of t, sometimes can be written as f of x comma t, with x of t naught is represented by x naught. That means, the initial state is represented by x of t naught, which is x naught, where x belongs to the n dimensional Euclidean space, it is a state vector, and t greater than equal to 0. Let x equal to x e be an equilibrium point such that f of x e equal to 0. Let us consider the origin is the equilibrium point of the system. So, in that case f of 0 equal to 0, x dot equal to 0 in that equilibrium point. So, which implies that the system will continue to be in equilibrium state x e equal to 0 for all time. Okay. So, this equilibrium point is said to be, I want to create a new slide here. Okay. So, let me erase this and write again. Okay, let me write here. So, this equilibrium point is said to be stable in the sense of Lyapunov, if we are able to select a bound on the initial condition, so that it will result in the state trajectory x of t that remain within a chosen finite bound. I repeat, the equilibrium point is said to be stable in the sense of Lyapunov if we are able to select a bound on the initial condition x naught that will result in the trajectory of the system x of t to be lying within a chosen boundary. Okay. So, this is the definition or basic concept of stability in the case of Lyapunov stability analysis. Now, coming to the point that we can explain this definition more formally, that the system described by the equation 1, which is x dot equal to f of x of t is stable in the sense of Lyapunov at x equal to x e, say it is x equal to 0 if for every real number, that is epsilon greater than 0, there exists a real number delta greater than 0 such that norm of x of 0 is less than delta results in x of t norm to be less than epsilon for all t greater than equal to 0. That means the initial, for any initial state x of 0 which is bounded by delta, which is the radius here, such that there exists a real number delta and epsilon such that the bounded x of 0 will result in the trajectory x of t to be within the stated boundary epsilon for all t. That means it will not cross this radius epsilon. So that means the system is stable at this equilibrium point in the sense of Lyapunov. Okay. So now let us talk about the asymptotic stability. What we can conclude about asymptotic stability? Here we can say that the system is said to be asymptotic stable at x equal to 0 if the state x of t approaches 0 as time approaches infinity. Then we can say that the system is asymptotically stable at the equilibrium point x e, which is 0 or origin in this case. If the trajectory, system trajectory stays within the boundary which is having the finite boundary limit of epsilon, then we can say the system is stable, but for an initial condition which is bounded, the state trajectory tries to come and settles in the equilibrium point x e, which is the origin at time, as time t approaches infinity, then we can say that the system is asymptotically stable in the sense of Lyapunov. Okay, now let us see the types of or the approaches that comes under Lyapunov stability theory. Lyapunov's first method is also called indirect method. We are going to see now, but before that, the Lyapunov first approach as well as the second approach gives an answer to the question how we can determine the stability of the equilibrium point x e without explicitly solving the dynamics of a system. Okay. So, let us see about the first or the indirect approach. Now, let us consider a non-linear system which is given by x dot equal to f of x. Now, expanding in Taylor series around origin or the equilibrium point x e, we get x dot equal to a into x plus g of x, where A is the Jacobian matrix of the function f of x that is given by A equal to dou f by dou x at x equal to x e, and g of x contains the higher order terms, that is limit mod x tends to 0 mod g of x upon mod x equal to 0, that is the case. Now, this is the case we started for a first approach method in Lyapunov. We can say that the first approach utilizes the Taylor series method in order to solve the question or in order to analyze the stability of a system. So, when we have the nonlinear system linearized to give x dot equal to a x plus g of x because of the Taylor series expansion, then the nonlinear system is asymptotically stable, if and only if the linear system, that is x dot equal to a x, is stable, that is if all the eigen values of matrix A have negative real parts, then we can conclude that the system x dot equal to f of x is asymptotically stable. And the advantages associated with this first approach of Lyapunov stability analysis is it is easy to apply. This approach is easy to apply. When we say advantages, definitely we have disadvantages also associated with this first approach. So, disadvantages: if in case the eigenvalues of matrix A, some of them are 0, then a concluding remark on the stability of a system is difficult. And also we can say that this approach is valid only if the initial conditions are close to the equilibrium point x c. Okay. Only if the, okay, so we can say that if this, another point is if the initial conditions are close to the point x e equilibrium point, but the question again raises how close is the term close is. Okay, so these are the difficulties associated with first approach. Then we will see the next approach called Lyapunov's second approach, or also it is called direct approach method or direct method. Now let us consider a nonlinear system given by x dot equal to f of x. Suppose that there exists an energy like function called Lyapunov function, say V of x, with the following properties such that number 1, V of x e 0. So, the function value at the equilibrium point is 0 and V of x is positive definite, okay, because we can say that V of x is a scalar positive definite function and V of x is greater than 0 for x not equal to x e. Likewise, we have the third property of this Lyapunov function candidate, V dot of x less than 0, which means negative definite. Then we can conclude that x e is asymptotically stable. Okay, so this is the mere intro about the second approach. Now, having given V of x, then we need to go for finding the V dot of x, the time derivative of the Lyapunov function candidate, which is given by V dot of x equal to dou V by dou x into x dot, which is equal to dou V by dou x into f of x, which is equal to dou V by dou x1 into f1 plus dou V by dou x2 into f of 2 plus it continues dou V by dou xn into fn. Now, this method has advantages which are given by it answers the question of stability of nonlinear systems without explicitly solving the dynamic equations. Question: how to solve the stability of non-linear systems without explicitly solving the dynamic equation of the system. Okay. Also, it has another advantage that it can easily handle time varying systems, that is x dot equal to f of x of t, and can determine, and also it can, this approach can determine the region of asymptotic stability or the domain of attraction of this system. Okay. It can determine the region of asymptotic stability or the domain of attraction of the equilibrium point. Now, coming to the disadvantages. The main disadvantage of direct method of Lyapunov stability theorem is there is no any systematic way to find or obtain Lyapunov function candidate. Another point is Lyapunov stability criterion provides only sufficient condition for stability. Okay, so that is the case. Now, let us see an example that involves both these approaches. Consider the non-linear system given by x1 dot equal to minus x2 plus a x1 x2 square and x2 dot equal to x1 minus b x1 square x2 with a not equal to b. Now, our goal of this problem to investigate stability of the equilibrium point of the system. In order to investigate the stability of the equilibrium point of the system, given a nonlinear system, we need to investigate the stability of the equilibrium point of the system. Now, the solution to this problem is, at the equilibrium point we have minus x2 plus a x1 x2 square equal to 0, x1 minus b x1 square x2 equal to 0. Okay. Now, multiply equation 1 by x1 and multiply equation 2 by x2 and sum them. That gives x1 square x2 square into a minus b equal to 0, from which x1 equal to 0 or x2 equal to 0. Here, which implies that x1 equal to 0 and x2 equal to 0 is the unique equilibrium point for the system. Okay. So, now let us talk about the linearized system at this equilibrium point. So, on linearizing this system at this equilibrium point x1 equal to x2 equal to 0 will give the linearized system x1 dot x2 dot equal to 0 minus 1 1 0 into x1 x2, which implies the characteristic equation determinant Si minus A equal to 0, that is S square plus 1 equal to 0, which implies S equal to plus or minus j omega, which means that the characteristic roots are purely imaginary. Purely imaginary. So, we cannot draw any conclusion on the stability of the nonlinear system using first method of Lyapunov approach. So, we need to go for using the second approach here. So, the second approach here is direct method that must involve using a Lyapunov function candidate. So, using Lyapunov direct method, let the Lyapunov function candidate is chosen as v of x equal to 1 by 2 x 1 square plus 1 by 2 x 2 square, which is a positive definite function and v of 0 equal to 0. So, the time derivative of this Lyapunov function candidate v dot of x is given by x 1 into minus x 2 plus a x 1 x 2 square plus x 2 into x 1 minus b x 1 square x 2, which implies upon simplification v dot equal to a minus b multiplied by x 1 square x 2 square. Therefore, we can say that if a less than b, v dot is negative. So, the system is stable. If a greater than b, v dot becomes greater than 0 for all x that belongs to the n dimensional Euclidean space. So, the system is unstable for a greater than b and stable for a less than b. We can also comment on the asymptotic stability of the system with this condition a less than b, because we can say that x dot x 1 equal to 0 and x 2 equal to 0 in this case. So, that leads to the equilibrium point being stable. So, we may say about that point, that condition case 1 can also be asymptotic stable. Now, let us see Lyapunov stability analysis of linear systems. Now, consider a linear system of the form x dot equal to Ax. Let us choose a Lyapunov function candidate in the quadratic form given by v of x equal to x transpose p x, where p is a symmetric positive definite matrix. Then we have v dot of x, okay, v dot of x equal to x dot transpose p x plus x transpose p x dot, a x transpose p x plus x transpose p a x. So, x transpose a transpose p x plus x transpose p a x. So, we can have x transpose taken out. So, a transpose p plus p a into x. So, that we can say that v dot of x equal to minus x transpose q x. Let us have like this, where what I did, a transpose p plus p a, I have represented it as minus q. Let us see. Here a transpose p plus P A equal to minus Q as per the previous equation. So, one thing we need to note that the system is asymptotically stable if the matrix Q is positive definite. Okay. One thing we have to note, A transpose P plus P A is also termed as Lyapunov matrix equation. The solution to this equation is P matrix. If the P matrix after solving is positive definite, then we can say that the system is asymptotically stable. Okay. So, for P to check it is positive definite, one can use Sylvester's approach. Okay. P must be positive definite, which means one of the conditions for P to be positive definite is that all the eigenvalues associated with the P matrix should be positive. Okay. Now, let us see an example associated with this problem. Okay. So, using the direct method, that is Lyapunov method, determine the stability of the system using MATLAB's M script. X dot equal to A x, where A equal to 0 1 1, 0.5 0 2, minus 3 minus 2 minus 5. Also find the corresponding Lyapunov matrix P. So, the solution to this problem is a MATLAB script. We know that Lyap is a function to solve the Lyapunov matrix equation to get P. Then Lyap command in the MATLAB solves the equation A x plus x A transpose equal to minus C, where input is A transpose instead of A for this inbuilt Lyap MATLAB command. So, the code is going to be A matrix, which is 0 1 1, 0.5, 0.2, sorry, it is 0.5, 0 and 2, 0 and 2, and then minus 3, oh sorry, it is minus 3, minus 2, minus 5, and let us say that Q equal to an identity matrix of size 3 cross 3. Now, P matrix can be obtained by the function Lyap of A transpose comma Q, and then we get the eigenvalues of P, that is all. Okay, so, we get the eigenvalues of P coming out to be all greater than 0, which implies that the system is asymptotically stable. Okay. So, that is all about this method. Now, let us see about the examples containing single link manipulator and an n degrees of freedom robotic system. Okay. So, now let us see how we can solve the Lyapunov function based control problem of robotic systems. Let us see here. Let us have the example of a single link manipulator, which is a problem of trajectory tracking. Okay. So, now here we have the single link manipulator's dynamic model coming out to be m L square theta double dot plus k theta dot plus m g L cos of theta is equal to tau. The tau is the joint torque, m is the mass of the link, L is the length of the link, okay, and k is the control gain. Okay. So, now let us see that what is going to happen to the system. Okay. All right. Let us see that. Okay. So, here we can see that we have to design a controller that will make the trajectory of this single link manipulator theta to track theta d. Okay. So, we need to design a controller via stability, Lyapunov stability analysis, so that the actual trajectory of the single link manipulator tracks theta d, this side trajectory. So, we define the error E equal to theta minus theta d. So, in that case E dot equal to theta double dot minus theta d dot, and E double dot equal to theta double dot minus theta d double dot. So, the above equation number 1 can be written in terms of the error as m L square E double dot plus k E dot plus m g L cos theta equal to tau, which is the error dynamic equation of the system. Now, let us choose a Lyapunov function candidate given by V equal to 1 by 2 m L square E dot square plus 1 by 2 k p into E square. So, if we have this Lyapunov function candidate which is having two terms, V equal to 1 by 2 m L square E dot square and half 1 by 2 k p E square, then we can have the derivative, that is a time derivative of this function, Lyapunov function, to be coming out as V dot equal to m L square E dot into E double dot plus k p E into E dot. Okay. Having taken E dot outside, we can say that it is E dot multiplied by u minus k E dot minus m g L cos theta plus k p E, where u equal to tau. Okay. That is the controller that we are going to choose in order to make V dot being less than 0 or negative definite. So, let us choose u as m g L cos theta minus k p E minus k d E dot as the control law in order to fit into the above equation for V dot, then V dot becomes minus of Kd plus K into E dot square, with the assumption that Kd plus K is greater than 0. With the assumption if Kd plus K greater than 0, then we have V dot less than 0, which implies that E dot tends to 0 and E double dot tends to 0, but it does not imply that E tends to 0. So, substituting this control into the aerodynamic equation, we get ml square E double dot plus K plus Kd into E dot plus Kp into E equal to 0. This implies that Kp E equal to 0, which means that E equal to 0. Okay. Because this aerodynamic equation, in that we are substituting the control law. So, we get, because theta dot equal to 0 and theta double dot equal to 0. So, we can have only Kp E equal to 0. So, error tends to 0. Finally, today we are going to see an n degrees of freedom problem. Okay, in 2 minutes we will finish that. Let us take the n degrees of freedom system, which is given by the manipulator dynamics m of theta into theta double dot plus c of theta into theta dot plus g of theta. This is equation 1, which represents the dynamic model of an n degrees of freedom robot manipulator, and take a control law tau equal to Kpe minus Kd theta dot plus g of theta is equation 2, with Kp and Kd are diagonal matrices. Okay. Now, it is a regulation problem. That means we are not forcing the robotic system to track a trajectory, rather we are making the robot to reach a goal point and stay there. That goal point is in the trajectory path. Okay, so we are considering a regulation problem here. So, in that case, now substituting this control law 2 into the dynamic model will give the closed loop system dynamics given by m of theta into theta double dot plus c of theta comma theta dot into theta dot plus Kd into theta dot plus Kp into theta is equal to Kp into theta d, which is equation number 3. So, having chosen the Lyapunov function candidate as V equal to 1 by 2 theta dot transpose m of theta into theta dot plus half E transpose Kp into E, that is equation number 4. So, let us consider this as the Lyapunov function candidate, where the first term is having the system parameters which involves the inertia matrix, and the second term has the error parameters. This function candidate is a scalar function and it is positive definite, and this function is always positive or 0 because the mass matrix m of theta and Kp are positive definite matrices. Now, differentiating the Lyapunov function candidate gives V dot equal to 1 by 2 theta dot transpose m dot of theta into theta dot plus theta dot transpose m of theta into theta double dot minus E transpose Kp into theta dot, which is again simplified into 1 by 2 theta dot transpose m dot of theta into theta dot minus theta dot transpose Kd into theta dot minus theta dot transpose C of theta comma theta dot into theta dot. Thus, it becomes minus theta dot transpose kd into theta dot. Now, we end up with only one term in the right hand side, that is v dot equal to minus theta dot transpose kd theta dot. From this equation we are coming to this, because there is a property that m dot minus 2 times c is a skew symmetric matrix, So, as per the properties of skew symmetric matrix, that x dot transpose, say, skew symmetric matrix S into x dot gives you 0. Because of that, we have m dot transpose into theta dot transpose into m dot minus 2 times c matrix into theta dot gives 0 in the previous equation. That is why we got, so we end up v dot is equal to minus theta dot transpose kd into theta dot. Okay. So, we can come to a conclusion that v dot is negative definite as long as kd is positive definite. So, next we need to investigate a final point, that here we need to investigate whether the system, robotic system, can get stuck with non-zero error. We need to check, that means the error must be 0, we need to confirm that, because v dot can remain 0 only if theta dot equal to 0 based trajectories, and the trajectory must also have theta dot double dot equal to 0, which means that v dot can remain 0 provided with the trajectories that is along theta dot equal to 0 and theta double dot equal to 0, and because Kp is non singular, we have from equation 2 that E equal to, that is Kp into E equal to 0, which implies, because Kp is non singular, we can conclude that the error E equal to 0. Thus, the control law which is given by equation 2, we can state that it can globally stabilize the system. So, we can say that the system is asymptotically stable by that controller given by equation 2, and Kp, this conclusion we have come from the system closed loop dynamic equation, that is basically from equation 3, not 2, it is from equation 3. We can say that this is the trajectory associated with theta dot equal to 0 and theta double dot equal to 0. So, we end up with Kp error equal to 0 from equation 3, from which we can conclude that error equal to 0. Okay. So, coming to the conclusion, that I can say that in this lecture we have seen Lyapunov stability theory with its methods, indirect and direct approach, and then we have seen examples associated with that. Then we have taken a linear system, and by using the Lyapunov matrix equation A transpose P plus Pa equal to minus Q, we could able to solve the stability of the linear system. And then we have seen the Lyapunov based control of robotic systems, which involves an n degrees of freedom manipulator and a single link manipulator. In the next class, we will be seeing about robot dynamics as well as the programming part. Thank you very much.